In this video, we'll be looking at the motion of a satellite or a moon around a planet. Now let's draw a planet. So here is our wonderfully blue planet, and around there, let's say there is a moon going around, and we'll assume it's a circular orbit with a radius between the centers of the moon and the planet being equal to r. Now it actually doesn't make any difference really if it's between the surface or the center, as due to such huge distances that the difference between the centers or the surfaces will be very, very small. Now we're going to assume that the moon is traveling with a velocity v, and the mass of the planet is big M, and the mass of the moon is little m. We're going to derive an equation that relates the radius r to the time period t. Okay, now first of all we'll look at the forces acting on the moon. Now the only force actually acting on the moon is the gravitational attraction F of the moon and the planet, which is of course equal and opposite to the force the planet feels on the moon, those two forces making Newton pairs. So let me just, it's easier, so I'm going to F there, radius r, rather distance between them r making radius r. So here we are, we've got the force acting on that planet, and we're going to look at the equations of motion for the force acting on there. Now what is actually happening? Well, that force F, okay, well, that force F is caused by the gravitational attraction, and the force is equal to the gravitational constant times the mass of the planet times the mass of the satellite or moon divided by the distance between them both, squared, r squared. So that is the force acting on it. Now that is acting in a circle, so it will feel a centripetal force. So it will cause a centripetal acceleration, and so therefore what you'll find is that this force F g m over r squared is responsible for a mass times acceleration, but it's a centripetal acceleration, so m times the velocity squared also over r. Okay, at this stage here we can cancel out the masses, so that therefore the mass of the satellite has got nothing to do with it, and we can get rid of an r squared in r, and that just becomes 1, which gives us gm over r equals b squared. But we want t in our equation. Now the time period is the time for one complete revolution, but also of course speed equals distance over time. Okay, now, and we of course got the speed here, v, or velocity, so velocity equals the distance. Now the distance of one complete revolution, now one complete revolution will happen in a time of t, one time period, so v is equal to 2 pi r over t, so the velocity equals distance over time, effectively. And we can use this here to substitute into that v, thus removing v and bringing in t into the equation. So I'll give myself a little bit of space, and I'll continue with the question. So here we go. So I will give myself a little space just here. So here we go. from here, gm over r is equal to v squared. Substitute a v into there, so that becomes gm over r equals 2 pi r all over the time period squared. So gm over r is equal to 4 pi squared r squared over t squared. And then we're going to rearrange that so t comes up, so t squared r comes up equals 4 pi squared r cubed, bring the gm down, over gm. So here we have a relationship between time period and radius cubed. And in fact, this here is a constant, so therefore the time period squared is proportional to the radius cubed. Or sometimes you may see it quoted slightly different, where they write it like this. Sometimes they'll write it as r cubed is equal to gm over 4 pi squared multiplied by t squared. So therefore, that's r cubed. So r cubed is proportional to t squared, and again that's a constant. So therefore, what it's showing is that the ratio of the distance between a planet and the moon cube is proportional to time it takes for an orbit, and that is Kepler's third law.